Welcome to our Compass seminar. It's a pleasure to introduce today's speaker, Natalie Perlin. Just a brief bio info. Natalie got her Master of Science from Russian State Hydrometeorological Institute, Hydromet, right? And the PhD comes from Tel Aviv University. And the topic of her studies was the changes in convection due to
land use effects on convective rainfall and increase of convection.
So that study was based mostly on observations, but then Natalie got interested in numerical modeling, and she did her postdoctoral postdoc at Oregon State, where she stayed as a research scientist until moving to RSMAS in 2014. Right. Natalie first had a joint appointment with CCS, so she did a lot of hard work on making sure that the computers at CCS work, and she still knows those computers very well. So if you have any questions, just right. Okay. Natalie published almost 20 papers, more than 20 papers, and topics ranging from the Gulf of Mexico, the oil spill, to RC interactions, and importance of mesoscale and atmosphere-ocean coupling. Natalie interests beyond science include, let me see if I can say it right, pastoral sport, horse riding. Right, Natalie competes with her horse, and his name is
Incognito.
Guido?
Incognito.
Incognito. Right. Natalie plays violin. Natalie knows how to sail. I have no idea how she managed to do all these things. But today she will talk about the study of mesoscale RC interaction in Southern Ocean using a regional coupled model.
Okay, thank you, Igor, for the extensive introduction. I'll try to speak louder, but I know it could be my issue that I speak softer, so please just let me know if you cannot hear me. I'll try to speak louder. So as Igor told, my topic today will be a study of mesoscale RC interaction in the Southern Ocean, and with particular implementation that we've done with the regional coupled model, developing it at RSMAS for this study. And the manpower behind this project were our RSMAS researchers, besides myself, Igor Kaminkovich, Hugh Gallo, and Ben Kirkman, who helped to design the domains, helped to run the cases and analyze the results, discuss them. And I also wanted to acknowledge right away other people and entities that were involved. So it was a funded NSF projects, the role of mesoscale ocean dynamics and RC coupling of the Southern Ocean, and now we're on the last year of Null Coast extension. And then besides the manpower and the brain power, we need computer power as well, because it's a modeling study. So it was done through the CCS initially, Center of Computational Science at and Pegasus was the main power horse for coupled model development, initial testing, and output analysis. However, most of the runs were done on Cheyenne HPC cluster. And Cheyenne is the cluster from NCAR, UCAR, CISL lab. And also I wanted to thank the team of ESMF, Earth System Modeling Framework. This is a coupler software that helped me to debug and go through numerical problems and overcome all the issues that we had. So the outline of my presentation will be the following. First, I will tell about the background on RC interaction and focus on the mesoscales, because there are different scales and different mechanisms at work. Then I present the two study domains in the Southern Ocean with two different regimes that we'll be focusing on in our numerical studies, and then present a regional numerical model itself, what it consists of, and a particular implementation for the Southern Ocean. And then it will be followed by discussing the model results of the temporal averages first, just to make sure, as a sanity check, that we get what we want. We do find some interesting features, mesoscale features, even in the temporal averages. Then I'll discuss how do we analyze the mesoscale anomalies and how we analyze the scale dependence. And then one of the last things will be how we're talking about how do we quantify the atmospheric response to SST variability. And it will be hopefully concluded by the summary conclusions. So the background will touch few issues, a few topics as a mesoscale SST variability, and the air-sea interaction could be seen in both eddy rich regions and the frontal regions, and they may have different mechanisms that work. Then, next, mechanisms of air-sea interaction. Then how do we quantify the atmospheric response to the SST variability? And I'll briefly touch the mesoscale variability in the climate studies, which is a very important topic if we want to represent the air-sea interaction correctly. So the background. So there are two different scales that we separate by how the ocean responds to the atmosphere, and vice versa. On the large scale, greater than 1,000 kilometers, it is so that the atmosphere is driving the ocean response. So the ocean is slowly changing to the atmosphere, large scale forcing. And it manifests itself in negative correlation between SST and the atmospheric winds, atmospheric turbulent heat fluxes. And the mechanisms for this feedback is, one of them is intensified winds. They cool the ocean surface via surface evaporation. And the second, if we have the stronger winds, it increases mixing, and the ocean mix layer may get deeper. That causes entrainment of the cooler water from the thermocline. However, on the mesoscales, when we go to the scales below 1,000 kilometers, so right now we talk about tenths, maybe hundreds to thousands of kilometers, the response becomes reverse, because now the ocean may drive the atmospheric response, and it manifests itself in positive correlations that are found between the SST anomalies and wind speed or wind speed derived variables and the heat fluxes. So the mechanism for that response is the increase of upward heat flux, decrease the stability of the atmosphere, and it causes higher mixing in the upper tropospheric layer. So higher mixing, increased turbulent mixing of heat, moisture, momentum in the atmospheric boundary layer may further lead to, if it has spatial and temporal scale large enough, they may lead to growing PBL height through mixing it with larger eddies. So we have larger eddies, they can lift the boundary layer height. Then if we have, again, strong SST gradients that can result in pressure changes, eventually we can get pressure gradients, and then the horizontal pressure gradients will result in secondary circulation, like similarly to the sea breezes, for example. So the good review paper for the different scales and different mechanisms and different studies is in Small et al. 2008 and numerous references therein. So let's look at the mesoscale atmospheric variability from space. Again, this was very important that the QuickScat satellite that launched in 1999 provided almost 10 years unprecedented coverage, almost coverage of the entire Earth on a daily basis, in some places even twice daily, of the ocean winds, with a resolution about like quarter degree. It's quite unprecedented, and that speed up the studies and the analysis of this mesoscale SST interaction. So the QuickScat measures the backscatter from the ocean surface. So it is then calibrated in terms of wind stress or neutral stability wind. Why neutral stability? Because we don't have any information about the stability in the near atmosphere. In the near troposphere, we only measure the backscattered signal. So right now we're looking at the figure from Shelton et al. Showing global 4-year averages. It was still when QuickScat was happily orbiting around. QuickScat data of divergence, wind stress curl on the top, and this is wind stress divergence, wind stress curl from the QuickScat data. Now, we can see that the regions where we know there are high mesoscale activity show the higher higher variables, and these are, I think these are anomalies. No, these are actual values. Now we can, in order to pick out the mesoscale signal, we can. This is wind stress curl. So this is a curl, a nominal value, and these are high-pass filtered values. So now we can see the mesoscale variability even better. So, for example, Gulf Stream or Kuroshio, Oyasho, like boundary, western boundary region, or the Southern Ocean in the Indian region, Agulhas return current. So they show even better. Okay, long way. Okay, right now I'm focusing on, I'm showing the small region of the Agulhas return current. Let me, in this area, with a lot of mesoscale, ADs, mesoscale activity. And we're looking at perturbation of QuickScat of neutral stability winds in, I think, in colors and meters per second. Yeah. So color is a perturbation equivalent neutral stability wind, and the contours are the SST on the same about quarter degree resolution. And these are anomalies that show up to line up pretty nicely. And the bottom plot is for the wind stress magnitude. This is equivalent neutral stability wind stress magnitude, and also SST. So they all show up pretty nicely. So that tells us that maybe we can quantify these anomalies. How do they, what is the ocean response? What is the atmosphere response to the ocean SST variability? And this is done by computing the coupling coefficient. So this is a new term I want to introduce, coupling coefficient. It's a measure of atmospheric response in terms of wind variable, whether it's wind stress, wind, or some derivatives of those, and the SST variability, whether it's SST self or the SST gradients. So this is usually done by using the bend regression of the for example, neutral stability wind perturbation on the SST perturbation. And this is the slope that we get from regression analysis. And I think the error bars here represent the standard deviation within this band for each band. And the bottom plot is for, I think, wind stress perturbation. And the middle plot shows it's like population of the band. So we have definitely higher areas with a very small anomaly. Yeah.
So the captions on these figures say that these are averages over long periods. Like this says
Yes.
7 years, and the previous figure was like 4 years or something. But I mean, aren't the eddies moving? Like, well, I don't understand how is the SSD fixed like that for 7 years?
No.
So why does the figure
just
look like that?
it just shows the correspondence. There could be bigger eddies, and that's how on the average they may look like. They may correspond.
So you just have some field and you average over 7 years, and
Yes.
it
Yes,
comes out
you
like
may.
that.
Yeah, you may. It has been thought that you need to get a clear picture. You need to average at least for 10 days, a month or longer.
Right.
My previous studies have done a month-long
Right.
simulation in this area, and this is something I got pretty similar picture.
Right.
But in our case, we've gone into even smaller scales, and we still can see these.
No, I guess but I'm saying like
But these are
if I
large.
take a picture of the SST of the ocean and I average over 7 years, isn't it gonna be like all smooth? I'm like, why do I have features? Why are there features there?
Stationary.
They're not average, right? Over 7
No, these are averaged.
over 10 days, 7 days.
No, these are for average for the entire period that would show up.
Okay.
Like in the previous picture.
Yeah, I mean I noticed it in this figure too. The
Yeah, you
averages
get
and the
it.
convergence. So there's all these little blips, all those little
Yeah.
features there. But
They're
somehow
not necessarily single feature. That might be a combined. That might be moving, like a transient feature, larger scale feature, that just manifests itself in co-variability in both SST and wind products.
They do sort of look like Zelfs, right? Like, right? No, but they're like the
Right.
the streaks.
No, I saw those kind of snapshots. Like,
This one is not a snapshot.
It's not?
No.
I guess I'm confused with another paper.
Yeah, sometimes it could be a snapshot. It doesn't really matter on these scales, I think. They are just persistent. So we're talking about the ubiquitous mesoscale covariability, and it's persistent. So how can you think about the wind stress curl and divergence, for example? How do they respond? What is their response to the SST changes? Imagine that you have some kind of a SST front with a cool on the top, warm on the bottom, for example, and you have that wind blowing over the water. So the wind would speed up over the warm water, right? So if it blows along the front where we have the cross front gradients, it will gain curl, right? If the wind will blow from cool to warm water across SST front, it will gain additional divergence, right? So the crosswind gradients will be associated or positive correlated with the wind stress curl, while the downwind gradients will be associated, positively correlated with wind stress divergence. And it works the opposite way in the southern hemisphere. So I was talking about the ocean eddy reach regions, but we also have the Gulf Stream, which is like a large frontal feature where we have some different mechanisms that show up nicely. Here is, for example, figure from Minobe et al. showing the wind convergence from the satellite wind convergence from ESMF over the Gulf Stream. And also, if you take the Laplacian of sea level pressure, that would indicate some kind of a secondary circulation response. You would also see the same signature of the Gulf Stream. Or if you can take negative SST Laplacian, you also will pick up this feature. And the negative SST Laplacian and sea level pressure Laplacian work like a proxy to like a spatial filters. So in this case, and we have two different mechanisms of air-sea adjustment to the SST. On the left, for example, the corresponding between the sea level pressure Laplacian will be related to the pressure adjustment mechanism, whereas the correspondent between negative SST Laplacian will correspond to the vertical mixing mechanism. And I'll talk about a little bit later and show what do we see from our studies. But this is quite unique area of Gulf Stream. There's only one Gulf Stream, as people say. And the ocean mesoscales also stand up in the climate studies. So these are the results from coupled numerical climate models, where on the left is for the case with the low resolution ocean model, whereas this one has the same atmospheric model resolution but high resolution at ocean model. So low resolution ocean, high resolution ocean. So and the color scheme is here for the correlation between the turbulent heat flux and the SST anomaly. So again, in the eddy rich regions or in Gulf Stream, we have much stronger positive correlation. Whereas when we have a low resolution ocean, they don't show up at all or barely show up, probably not at all. And these two show the correlation between the turbulent heat flux and SST tendency, which means it shows how the ocean is driven by the atmosphere because it's slow to respond. So in the case of high resolution case, we don't see much of the correspondence much of the lag between the SST tendency and the turbulent heat flux. So right here, so the nominal value of the correlation decreases, so from negative it becomes closer to zero. So high resolution and the ocean eddy mesoscale activity is important for the climate studies as well. Yeah.
What, high and low resolution relative to what, like, is it comparable to the atmospheric resolution, or what's the comparison?
Yeah, I think, sorry. Yeah, I think here is like 1 degree, and here I think it's 0.1 degree.
And then what about the atmosphere?
Atmosphere maybe 0.5, either 0.1 or 0.5.
Okay. So the right would be where they're roughly the same? I heard you right?
No, the ocean picks up more.
Oh,
Compared to the atmosphere.
Yeah,
Compared to the
atmosphere is the same.
Yeah, I'm just wondering how they
cases.
compare to each other's resolution. So is the left one, the ocean resolution is worse than the atmosphere's, and the right
Yeah, I
one,
think
the
so.
ocean is higher? Or
I think they may be, no, I think they're the same 1 degree.
okay, so they're both the
Yeah.
same on the left, and the ocean's higher than the atmosphere on the right.
Is it right? Yeah. Is it right?
Yeah.
I think so.
It's about 0.5 in the atmosphere in both cases.
So it's 0.5.
I think so.
Okay, yeah, these are the details. Yeah, so it's 0.5 with the atmosphere in both cases, and here is 0.1 for the ocean and 0.1. 1 for the ocean, 0.1 for the high resolution. Low resolution 1, high resolution 0.1 ocean. So yeah, I see what you're saying.
Yeah.
So here we have the ocean lower than the atmosphere, and here the ocean resolution is higher
Okay.
than the atmosphere. Yeah. So the next one. So as I show you that there is a lot of eddy activities in the Southern Ocean, especially like in Agulhas current, that are picked up by the satellites and show up in a larger time scales. We decided to look at the two different study domains that have different time regimes. One study domain is in the Pacific with the shallow SST meridional gradients, and another has rich eddy activities and strong SST meridional gradients that correspond to strong current. So Indian Ocean, and they will be referred to like weak current WC or strong current SC. So our ocean atmosphere model finally consists of three major components. So COAMS is the atmospheric model component of the US Navy. It's called coupled ocean atmosphere model, but it's actually for over a decade or even maybe a couple of decades. Only the atmospheric component was available to everybody to use until recently. And it's non-hydrostatic, fully compressible equations, Arakawa-Sig grid, staggering, for numerical schemes, many physical parameterizations, including the Kane-Fridge scheme for convection, convective precipitation for the scales less than 10, larger than 10 kilometers. So the ocean is the regional ocean component, and is Rom's model well used again in the community, modeling communities, hydrostatic free surface terrain following ocean model based on primitive equations. And the ESMF is a main coupler that is used to take care of the synchronization between these two. ESMF is the Earth System Modeling Framework, and it synchronizes, enables the exchange of the variables between the main components. So it exchanges, it receives the momentum, net heat flux, and solar heat fluxes from the atmosphere, transfer it to the ocean, does the regrading to the correct resolution, and transfer it to the ocean, and then it receives SST from the ocean and prepare it for the transfer to the atmosphere. And there is another, I put it in parentheses, there is another piece of special domain created specifically to perform the SST fields blending, because the ocean domain covers only part of the atmospheric grid, and the SST information for the outer regions need to come from elsewhere, from observations. So this coupling approach is described in our two papers. At that time it was implemented with a different coupler, model coupling toolkit, and recently, for the last few years, we use the more advanced ESMF software to take care of various aspects of the coupling. So, and here are our two study domains. So right now I'm just showing a snapshot of SST from this comes from the satellite, and this comes from the ocean model after the spin up. I'll talk about, a little bit later about it, but right now you can show that the outer grid is the atmospheric domain that spans almost 30 degrees. There is a nested domain with 1:3 ratio in horizontal resolution. So outer domain was 27, inner nested domain is 9 kilometers. And the ocean domain occupies a part of the nested domain, and it's where the exchange of the SST takes place. Now, we need some kind of perform some kind of a blending between the ocean result SST and actual SST, and this is done with the grid 3, the additional piece of additional grid that is created just solely for exchange. So the SST for the outer grid and part of the atmospheric inner grid come from ocean optimal interpolation and NASA SST analysis with a 40-degree grid. And the fields here come from the spin up of the ocean after multi-year runs, first with the just driving with the climate driven by climatology, and second after spin up using the coupled run. So we start our actual run that we analyzed after multi-year spin up with the ocean only, and then with a coupled model. So these are SST fields in the beginning of our coupled run. And these are some additional information about these two, about the setup of the two main gridded components, with the resolution 27 and 9. In the ocean we have 2.5. Then 49 vertical levels in the atmosphere with 72-second time step. Then initial and lateral boundary conditions for the outer grid comes from 6-hour updates. So they updated every 6 hours from the quarter-degree global FNL and GFS analysis. So we have it. I saved it, download it regularly for a period of 2 years. So it's we use it to force our model with a real atmosphere. But the thing is that the ocean domain is essentially a semi-idealized model with the zonal flow in the Southern Ocean. So it's like a channel, except long channel, 2,800 kilometers by 1120 kilometers in zonal and meridional direction. But instead of being just a plain channel, we have, with a maximal depth of 3,000 meters, we have several randomized seamounts to make sure we have the transport consistent with the estimates from the climatology. So realistic transport through the area. And it's nationalized from climatology, and it has the periodic boundary conditions east-west and the sponge boundary conditions on the north and southern boundaries. And when we, during the coupling, we gradually reduce the sponge layer. So it's more, it uses more the, Igor, I need some help with that. With the sponge layers, how do they change?
Yeah, the sponge layers keep the large-scale stratification close.
Yeah,
to
but
what we
they
want.
also decrease in depth.
Right. So near the surface and not as.
Yeah, near the surface there is less nudging to the climatology.
Natalie?
Yeah.
Why such long spin-off for the ocean? I saw 24 years for weak current and 12 years for strong.
Yes, that's correct.
Why?
We wanted to make sure we have the correct volume
Okay.
transport. It's speed up.
I would say the spin up is very short. Actually, it takes a while for the ocean to equilibrate, but a couple of decades should be enough for the upper ocean. But if you want a full equilibration, it should have been achieved.
Yeah, so it's not.
Sounds like a lot.
Yeah.
By ocean
Yeah, for the
standards, it's
atmosphere.
extremely short. So.
So again, we not only couple it right away and start analyzing, we do spin up ocean only, then here spin up with a coupled system, and then the 2-year control runs. So these are how the potential density look like. Average meridional, average zonally, so in meridional direction. Oh, sorry. So in a weak current, we have not too steep isopycnals, so that correspond to pretty weak current. And in the second region, we have very steeply sloping isopycnals, so we get a strong current naturally. And these are from the 2-year coupled run, the average. So now let's look at some mean statistics and what we can see from here. So from now on, the left column would show weak current and the right column would show data for the strong current. So the SST contours for the mean and the SST standard deviations and are in color scheme, and in all other plots also mean values are always the lines and the color scheme for standard deviation. So again, SST is more zonal and weak current, except few regions here, and we can see very strong meridional departures in the strong current regions in the SST, and areas of reduced and increased SST variability on the mean. So, but that's with SST. If we look at the atmosphere, even in the atmosphere, so here is the atmospheric temperature on the left, weak current, not much zonal variability, but in the strong current, we can see some meridional departures even in the mean atmospheric field. So it's realistic field coming from the larger model, and it still feels the SST changes, both in the mean fields and in the variability. Now, if we look at the difference, it stands out even more. So we do have some positive maximum in the weak current, but in the strong current, it's over 2 degree difference. It's like a permanent feature. And the same, this is the wind strength vectors, standard deviation, and the temporal averaging contours. Again, these mesoscale features are quite strong here, with even the local minima and maxima showing up. A little bit more fields again, just to show the difference between the two regions. So these are the turbulent sensible heat fluxes and latent heat fluxes. And look at this huge anomalies of positive fluxes. What else? The atmospheric turbulent kinetic energy. So from the last two model levels, also 10 meters, and the next I think it's 50 meters. And even in the turbulent kinetic energy, 2-year average, you can see these sending features in the TKE, atmospheric TKE. Moreover, if we look at the atmospheric boundary layer height, so what do we see? We have some positive, we have some local maximum here, but in the strong current, look at this 900 isolines. They correspond to the features we can see in all other fields. I think that's pretty pretty outstanding. So in the ocean, we have ocean currents. The upper plot shows ocean currents and contours of free surface of zeta. Weak current, strong current. So we do have strong currents on most of the domain here, and in the eddy kinetic energy, it shows pretty nicely the mesoscale features again. And adiabatic energy, I just put a note here that it's determined as a local departure from the box filter spatial average with a 300 kilometers grid box size. Now for the another variable diagnostic ocean mixed layer depth, which is computed from the daily average profiles of potential density and determined as a threshold of the level where we exceed, where the sigma theta exceeds 0.3 kilograms per meter cube. So this is like a threshold for a mixed layer depth, and we can see that a mixed layer depth, for example, in the weak current, we do have stronger, deeper mixed layer where we have stronger currents, but in the strong current area, we have a deeper mixed layer over the areas of positive, both SST and wind stress anomalies. So we have several mixed mechanisms working here. Okay, so now as I show you, we have several mix of scales, and maybe in our study we can study the scale dependence of these anomalies. So, and how do atmospheric coupling depend on the scale of the SST perturbations? And we can separate the scale by doing the different spatial filtering with different sizes. And here I denote F2 and F1 and F2 as spatial 2D filters. It's a two-dimensional lowest quadratic filter that smooths. Smooth is a field in the spatial scale, and with F1 the half span window is 10 degrees by 5 degrees in the light and long direction, which is roughly half of the ocean domain. And in the second filter, F2 has a much smaller half span window of 150 by 150 kilometers. So our anomalies will be determined as the local values less their filtered or smooth values. And in this case, perturbations could be said as anomalies, or could be referred to as high-pass filter values. They all mean the same thing. So high-pass filter value. So first we can examine what do we see in the power spectra when we use these filters. The power spectra here shows the meridional average of the SST. I think this is wind stress, and this is the flux, turbulent heat flux, I believe. Yes. And so I use every latitudinal line, compute the power spectra, and then average over all of them. So it's meridionally averaged zonal spectrum. Yes. The solid lines are for the strong current, dashed lines for the weak current. The black lines are for the full fields, red for the F1 and blue for F2. So we can notice here that F1 not only cuts pretty nicely, but it also illuminates the peak at 400 kilometers in all the fields, which is apparently is a characteristic time scale, a length scale of the anomalies at this domain. The F2 filter, for example, it just cuts the power. So apparently, it doesn't pick up the specific scale. It just cuts wherever it cuts the power wherever we told it to. And a few more things to look at are the differences between the power spectra in SST and turbulent heat fluxes, where there are differences between weak current and strong current. Whereas in the wind stress, we don't see much of the difference between two cases. Again, that was the average. So now we're getting to the actual anomalies. So these are how the anomalies that we analyze look like. So these are the 5-day average high-pass filtered anomalies of the wind stress in color and SST contours in SST contours. Dashed negative, I think this is 0 contours, another are positive. So they do correspond, so weak study case, weak current, strong current, filter 1, filter 2. So again, you can see the anomalies are pretty large and they correspond, but not 100%. So there is some visual correspondence, but not 100%. Now, because we have 2-year run, we essentially have 735 days, and we do 5-day running average. That leaves us with 731 day of these snapshots. 731 snapshot of this figure, these types. So we can analyze it and quantify it. So we have large data, much larger data compared to the observations or even smaller scale studies. And we are free to choose the different type of filtering to suit our quest for scale dependence study. Now the F2 features, you can see that they become much more smaller, even though they're still aligned. Again, not 100%, but they do align very well. But they are smaller. Now, the previous was for the wind stresses. This is for the turbulent heat flux. The same day, January 15, 2017, but for turbulent heat fluxes, and these anomalies align much better. So they have a much better correspondence than the SST and the wind stress, which is not surprising, but this is something that we wanted to check. Again, if you remember the background, so the turbulent heat flux basically what drives the mesoscale anomaly, and by increasing the mixing, increasing turbulent transfer. Now we can compute correlations between these fields, correlations between these snapshots. So in color, you can see the correlation between SST anomalies and wind stress perturbation for filter 1 and filter 2. But in contours, this is something interesting. These are correlations between the actual fields, unfiltered data of the SST and wind stress, but with the annual cycle removed. So the correlations between the full fields are mostly negative everywhere, except some small regions. But correlations between the filtered data are stronger for the larger scale anomalies. Interestingly, for the smaller scale anomalies, they're reduced. This was for wind perturbations. The similar for the heat flux, correlations between the F1 filtered data and F2 filtered data. So F2 filtered data, we get a little bit smaller correlations. However, the correlation between full fields showed in color, black positive, gray negative, are somewhat in between. They vary. They're small, but can be positive or negative. So but correlations between the filtered are strongly positive, especially for the F1 for the larger filter. So now I wanted to, maybe I'll skip that. I just wanted to say what do we use for the quantification. So we use wind speed, and we actually don't use the actual wind speed. We use neutral stability wind that doesn't have the stability dependence term. So it just uses U star modeled by the atmospheric surface layer over K and the logarithm. And then we use wind stress curl and divergence as wind stress derivatives and look at the correlations. And the coupling coefficients. So these are the coupling coefficients as one of the previous studies showed for the smaller region and for the larger time average. So the upper is for wind stress anomalies versus SST. Again, this is weak current, strong current. Wind stress anomalies versus SST in black, and the blue shows the beam population. Again, you can tell the smallest beam that we count has 1,000 points. Then others have, I think, over 10 and 7, something like that. These are the equivalent neutral wind anomalies versus SST, and these are two more: wind stress divergence versus SST gradient, wind stress curl versus SST gradients. And the error bars here represent the standard deviation within the bin. And interestingly, so they all show linear relationship, even though the wind stress doesn't show much difference. I think it's 2-0 for the gray. Okay. F1, F2. Yeah, it's filter 1. We have the larger range of perturbations and the 2-0 here. And filter 2 has a smaller range of perturbations because we have smaller anomalies. So for the wind anomalies, we have, interestingly, correlation coefficients higher for the wind current than for the strong current case. And this is pretty consistent in all of the correlations. I even had the table. Just don't look at the numbers. I try to highlight and to explore how the correlation and coupling coefficient, how do they relate to each other? Because you can also estimate, instead of using Bing correlations, you can use some kind of bulk formula where the correlation coefficient will be expressed in terms of coupling coefficient will be expressed in terms of correlation coefficient, and then the standard deviation of U anomaly over the T anomaly. So look at the top two lines. This is the coupling coefficient for SU, which is higher in low S2 and F1 and F2, but the correlation coefficient is stronger for the strong eddy or strong current case. So coupling coefficient is stronger for the weak current case, but the coupling coefficient is stronger for the strong current case. And this is true for all the variables. And even if I don't show it, but I try to separate domain, strong current domain into north part and south part, and see if it makes any difference. And it doesn't make a difference. We always have the stronger correlations in the strong current and stronger coupling in the weak current domain. So I also explored some dependence of wind coupling coefficient on the actual wind speed. So this is not the perturbation, but the actual wind speed. But first I wanted to see what is the PDF of what is the range of the wind speeds that we resolve in our model, that we have in our model. And most of them, within 4 or 5%, they fall. Like 5% is less than 4 meters per second, or I think, yeah, 4 meters per second, and another 4 or 5% of the top is like larger than 50 meters per second. So this is the PDF. This is cumulative distributed CDF function for different weak current and strong current. D1 and D2 denote here for different domains. Domain 1, we usually do the analysis for domain 2, but we wanted to make sure they're consistent. So we do see that for the strong current we have stronger winds everywhere. So I did some analysis of the dependence of these coupling coefficients on the winds, on the background wind, and not only the coupling coefficients themselves, but the terms, right? The correlation and the standard deviation. So what do we see here? So these two panels are the coupling coefficient for wind stress and wind speed for the strong eddy case, and this is for, let me see. I think this is for filter 1, this is for filter 1, this is for filter 2, sorry. That's the only one place where we depart from the convention. So this is for filter 1, this is for filter 2. So let's focus just on filter 1. So wind speed coupling coefficient appears to be pretty high at the intermediate time wind speeds, and lower on both ends of the spectra. And there is stronger coupling coefficient for the weak current case, as what we expected to see. But for the wind stress, interesting, we have nearly linear dependence. Pretty surprising. And we wanted to see why it could happen. And I plotted here the terms of this equation. So the blue line is the coupling coefficient again. The correlation coefficient is, I think, okay. This is coupling coefficient, this is correlation coefficient, and these are the two standard deviations. So you can see that in this case, for the weak current, correlation coefficient does follow the same curve. So there is no surprises why the coupling coefficient is following the same case as correlation coefficient. But for the strong eddy case, the correlation coefficient in dashed does show the same structure as the weak current case, but different response or different standard deviations of the U and V, what lead it to be less wind speed dependent. Like in the winds, let me see. This is wind speed. I think, yeah, it's wind speed, but the correlation coefficient is for the wind stress. Yes, for the stress, we get the coupling coefficient, these lines, mostly linear, but the correlation coefficient are similar to what we see with what we saw in the winds. And this is because we get linear relation between the linear dependence on the coupling coefficient is because the dependence of sigma. I think it's sigma SST or sigma U that shows dependence of ENS, dependence of, it increases with wind speed. In other words, it leads to this linear dependence that we see in the coupling coefficient. And for the F2, it's just a little bit skewed. It's the same idea. So in the last slide, there are two mechanisms that I was talking about with the vertical mixing mechanism and the pressure adjustment mechanism. And the upper two plots show the correlation between the Laplacian on the sea level pressure and wind stress convergence that show positive correlation, even though they are stronger in the weak current case. That would mean that there is stronger pressure adjustment mechanism on the weak current case. However, when we use the proxy for detecting the vertical mixing mechanism that was used in other studies, using the correlation between the negative Laplacian of SST and the wind convergence, we don't see much. So there's nearly none, but we already know that they are present because we detected them from other studies, from the analysis of different scales. But this is important to know that yes, it's the mechanism is there, but it's not easy to detect it because it's not collocated. We have to study maybe individual squall lines or individual events to understand it. This gives us on average picture that yes, it's present. So, and the final summary and conclusions of the talk are the following. So we have successfully implemented the regional model for our study with a realistic atmosphere and ideal ocean model. And we successfully modeled the two regions of the Southern Ocean with different regimes, strong current and weak current case, and where we detect the large mesoscale and small mesoscale anomalies present. They could be either stationary that we can see in the mean field, or they could be present, or they could be transient that we can detect with the anomalies, sequence of anomalies snapshots. And then the coupling coefficient and temporal correlations are good quantification of the atmospheric response to SST changes, and we get a stronger wind coupling coefficients for the weak current case, surprisingly, than for the strong current case. But this is for coupling coefficient. For the correlation coefficient, they are reversed. And then we also found that equivalent neutral stability winds and wind coupling coefficient are quite a consistent, show a more consistent dependence on background winds than wind stress, for example. And then we also detected there are two mechanisms of atmospheric wind response to the SST anomalies that are present, both vertical mixing mechanism and the pressure adjustment mechanism. And we have big plans for more studies, but so far this was a first time presentation of our model. Okay, this is extra. Okay, thank you. Let's stay the whole hour.
Questions for Natalie?
Yeah.
Go back. You just showed that figure with the linear showing the coupling coefficient.
Yes.
Right, between wind stress and wind speed.
Yes.
Right. So I guess I'm trying to understand. In the model, there's a formula for wind stress as a function of wind speed. Right.
Yes.
I mean, that's in the model. But is that just showing the formula, or is it showing something different?
We are talking about the wind stress coupling coefficient, which quantifies the atmospheric response, which is determined from the anomalies. They are not involve the actual values; they only involve the anomalies.
So this is sort of showing a trend in deviations from what we would expect the baseline behavior. like the base,
Yes, yes.
right? Because the model, there's a
Yes,
formula,
and
right?
this is that
Yeah.
means that the atmospheric wind stress becomes more sensitive.
Okay.
And this is a couple coefficient, so it's a response to SST.
SST
Right.
anomaly.
SST goes up,
Yeah,
the mixing increases, you get more.
but it's not only SST goes up. It gets a local anomaly. It's local perturbation.
Yeah,
I know
mean-
it's a little bit.
It can't be going up everywhere. It has to be on go.
Yes, it has to be an anomaly. Anomaly corresponds to anomaly. Yeah, this is a tricky one. And I did it for the turbulent fluxes, but they're also nearly linear. But it's more straightforward. With fluxes, it's more clear. With the wind stress, it wasn't as obvious. The studies showed, yes, there is a dependence, and but it varies regionally, it varies with seasons. I also look at some seasonality of these coupling coefficients, and you do see more seasonality in wind stress than in wind speed, ENS wind speed coupling coefficient. So yeah, the wind speed coupling coefficient, ENS wind, they seem to be more stable representation than the other types. Yeah.
How do you expect your results to change if you include currents in your coupling?
I don't expect them to change much. I was thinking about that, but how can you you have all the over open ocean. Look at the look at the wind speed. Most of the winds are between 4 meter and 50 meter per second, or like 95% are stronger than that. And we have maybe 20 centimeter per second current, and I don't think it would change much with the current. It may, but I think the greater effects we may get from including like a wave model.
20 centimeter per second current, is that a mean, multi-year
Mean.
mean? Or?
Yeah, it's mean. I haven't looked. Yeah, that's right.
Okay,
I haven't
but
looked
actual
at
values are the ones that matter. And in the regions that you look at, you easily have 1 to 2 meter per second currents.
Right.
I'm talking about reload.
Yeah, I don't know. Igor may know more about that, but these are the values for Gulf Stream, not for the eddy regions. It's not a frontal region.
Individual eddies may be as strong as 1 meter per second, it's usually
Yeah.
bigger. And the winds are strong in the southern ocean, so the difference is really large. But it's a good point. The coupling in standard coupling in quants does not account for the ocean.
No,
currents.
I was thinking about to include it, but you pass. Yeah, the thing is that you pass the wind stress from the atmosphere. If you need to include the ocean, you have to modify it. It won't be computed from the resulting wind. We get not wind from the atmosphere, we get the wind stress already. So I'm not
maybe
sure.
you need to get currents to the atmosphere.
Yeah, you'd have to know the currents.
Yes, you have to know the currents, but the currents are at the surface, not on 10 meters. And the wind at 10 meters is what is used to derive the wind stress. So how do you adjust
So
for the height?
Is your 10 meters lowest layer or
Yes,
reference
yes, it's
height?
lowest layer.
I see no issue. That's what you use.
Yeah, we can try it. It's a model. We can do whatever.
Yeah, I was thinking about that, but it would definitely be an issue for the Gulf Stream.
Oh yeah.
But for the again with these winds, and again this is not a climatology with a persistent wind. blowing in the same direction, we have the very stochastic forcing with the synoptic systems propagating through the area all the time in different directions. I mean, it's mostly westward, of course, but they could they could not be in the same direction as the wind, as the current.
And they could be against. Currents could be against the wind, so
Yes,
you could
exactly.
your effect could go either way.
Yeah, that's something that
And
definitely can
you have
play
all
a
the
role.
pieces, and
Um,
you know that the mechanism would be more correct than what you're doing now.
so what you do then? You subtract the
You
current
use-
at the zero
Right.
level from the
Yeah.
wind at the 10 years.
You use relative wind speed relative to the current, using vector quantities in both heat fluxes and momentum. That's it.
Yeah. For the heat fluxes, the effect, if I mean, the effect is usually negligible for the heat flux itself, but for the mechanical energy, it can be substantial. But again, this is thousand oceans. The winds are much stronger than the ocean currents. So the effect is can be strong in mid latitudes, right? But yeah, it
I'm mostly
could be something
concerned.
we can look
I
at.
would be more concerned about the waves, what the wind-wave interaction will do to the coupling.
Yeah, but that's the part you don't have.
Yeah, I don't have.
You have
I mean,
currents.
I
Yeah, that's fair.
did once the coupling between Swan and Roms, but it wasn't productive or didn't go into production.
It's sure not easy.
Yeah. Yeah, but this is something I thought about, but it would require more overhead work.
You can only do so much.
Yeah.
I know.
But thanks. Okay, thank you. I hope you learned a little bit. I hope you learned a little bit of mesoscale and different types of
I did.
interactions. Thanks.
Thanks.